Before we move on to the next step of learning about z-tests, we need to get a little statistical theory under our belts. And this statistical theory involves the distribution of sample means and the central limit theorem. The distribution of sample means is all of the sample means for all possible random samples of a particular sample size of n that can be obtained from a population. Now, let's break that down. Let's start with something we already know. We know about a distribution of scores, of raw scores, and they form the normal curve, this bell-shaped curve that we've used several times before. So every score is represented underneath the bell curve. Well, what if instead of creating a distribution with just raw scores, we started doing sample means? So in order to gather these sample means, what we would need to do is start by establishing a sample size. Let's say it's 10. So we have a population of 100 people, and we want to obtain every possible random sample of a sample size of 10 that could come from that population. So how many samples would that be? What you might do is simply do some easy math and say, well, there's a sample size of 10, population size is 100, so we could do 10 samples. And that would be incorrect because we sample with replacement, which means that after we do a sample, all of those people would go back into the population and we would draw our next random sample. It may or may not include people who had been sampled previously. So what would happen is we wouldn't just have 10 samples, we'd have hundreds of samples because there are a variety of samples that could be drawn of a sample size 10 from that population of 100. What we would do for every sample is compute the mean, and we would create a distribution of those sample means. Now, as you probably have figured out, those sample means would tend to stack up around the population mean. A few of them, by random chance, would be far away from the mean, and they would have a very low probability. Those would be values that are far high above the mean or low below the mean. Most of the scores are going to be near the mean, toward the middle. So a distribution of sample means is just all of the sample means that could be collected. We choose a sample size, n, find all of the possible random samples from a particular population, and then we create this distribution of sample means. So in this example, each of the small boxes here represents the mean obtained for one sample, and they also form this normal curve. Well, this brings us to the central limit theorem, because in every sample, there's going to be some sampling error. But sampling error is a function of sample size, such that the larger your sample size, the smaller your sampling error. As sample size increases, sampling error decreases. So if I were to ask you how tall is the average American male, and you just looked around and asked the first person that you saw, the first male, how good would that sample of size 1 be in telling me about all males? It could be quite off. But what if you sampled a second person and then averaged their scores? We're going to decrease the error a little bit. How about if you sampled 10 males and got all of their sizes, all of their heights, and divided by 10? Then you're getting better. What if it was 100 or 1,000? See, if you get enough, you would actually have the entire population. So the more people that you're sampling, the more that your sample begins to look like the population. As your sample size increases, the sampling error, the way that your sample differs from the population, decreases. Now, the central limit theorem says that as sample size increases, that distribution of sample means that we just looked about becomes more normally distributed, and that is what we want. Another idea that we need to have in mind is something called the standard error of the mean, which is very similar to standard deviation, only it has to do with the samples that we've been talking about. So, standard deviation, this sigma figure, that represents the average amount of variability between any raw score and the sample mean. that we could expect by chance. The standard error of the mean is the average amount of variability between a sample mean and the population mean that is reasonable to expect by chance. So in the same way that the standard deviation tells us about variability between raw scores and sample means, the standard error of the mean tells us about variability between sample means and population means. So hopefully you can see that the standard error of the mean is equivalent to, or the same basic idea as, a standard deviation. However, there's one other thing that we need to know about this standard error of the mean. The standard error of the mean uses sigma, but divides it by the square root of the sample size. So here's what you would need to know. When it comes to sample size, the bigger, the better. The larger your sample, the closer that is going to match the population. However, you don't need a sample that's dramatically huge. If you get above sample sizes of 30, you start approaching normality in your distribution of sample means. So, if you are doing a simple test, having more than 30 subjects is a good minimum to shoot for. There are things like power and effect size that we can go into later on and talk about how to more clearly dial in that number. But if you want a quick and easy estimate of how many people do you need in your sample, 30 should be your minimum. This standard error of the mean formula we see at the bottom of this slide. It's the sigma sub m. Standard error of the mean is sigma divided by the square root of n. And that is what we're going to use for our t-test. And the t-test is what we're going to learn about next.